So can we start now?
Yeah, yeah. So I've just joined in. So maybe I just try to share my screen once. Okay, so let's
Okay.
see
Okay.
what works. Is it visible? Is my screen
Yeah.
visible? Okay. Okay. So in that case, I'm unset. So just let me know when we'll start.
Okay, welcome everyone to our workshop. Now our speaker is Professor Debdeep Mukhopadhyay. He has already delivered a talk on hardware security in the connected world on the very first day of our workshop. Now it's over to you, sir.
Okay. Thank you very much. So in today's talk, I will try to talk about like some work that we have been doing on lightweight block ciphers or developing lightweight block ciphers, and we have been able to kind of apply some of the cellular automata based techniques. So I thought that that would be pertinent for this workshop, which addresses this topic of CA as well as secured hardware design. So I will try to kind of take the or look at the problem from the aspect of a hardware security designer and see that where CA can be useful, and not like from the other side. So let's see how we can develop this talk. So we all know that security is of importance, and because of the fact that we have like this new generation networks like Internet of Things and so on, which shows us that security is a growingly important issue because of just to give some examples of automobile hackings, illegal surveillance, camera manipulation, and there may be manifold similar kind of scenarios where security is of paramount importance. So encryption is an effective countermeasure. IoT is now required to apply encryption to sensor devices, and these devices are in environments with various restrictions that have not previously been subject to. So therefore, right, that makes lightweight cryptography an extremely important field of research. So it's basically like not only like to develop theoretical ideas, but also to translate them to real life products. So so what is lightweight cryptography? Okay, so maybe I should have asked this question, like, am I audible? Like, are you able to hear me properly? Yes. Hello.
Yes, sir. Yes,
Okay.
sir.
Okay.
Although
Okay.
we can't see you.
Yeah, I mean my camera is off actually, but I think you are able to hear me, right? Okay.
Yeah,
Yeah.
yeah,
Okay.
yes.
Okay. So the lightweight cryptography essentially is is a cryptography which is specifically chosen for extremely constrained devices. So for instance, where you have got requirements of less area, low power consumption, in such cases, the crypto that you need to develop is extremely important because you cannot trade off security. At the same time, you cannot afford traditional cryptography. So therefore, right, I mean, we try to kind of bring down some of the requirements which probably traditional cryptography will also occur. So we are not really intended here to defend against an all powerful adversary, but more importantly, practical adversaries need to be mitigated. And the edge devices in the Internet of Things or cyber physical systems need cryptography. So that is something that we all understand, that it is extremely crucial that we need to provide the adequate amount of crypto to these resource constant devices. So that motivates us like to look into various kinds of devices where and it's very important that we need to understand the platform, because every platform comes with its requirements. For example, some platform may say that less memory is important, some may say less computing power is important, some may say I need to work on low power supply, and so on. But all of them contain sensitive information, and therefore we need to adapt our cryptographic algorithm or traditional cryptography to suit such requirements, and that essentially defines this topic of what are called as lightweight cryptography. So just to give you some examples, so these are examples which are taken for specifically for sensor devices. Okay, so there are many such kind of platforms. For example, like if you are looking into some Atmega cards, which may have an 8-bit processing unit for operating on 4 megahertz, have a 4 kilobyte SRAM. So likewise, you can have, like it can range over some microcontrollers like MC68328 or Dragon Balls, which may have a 32-bit microprocessor operating on slightly higher frequency, maybe 60 megahertz, to say MIPS. For instance, like it will probably have 64-bit and operating on 8 megahertz. So there is a wide range, but still all of them have limited processing capabilities, and we need to kind of apply or like develop cryptography to suit such requirements. So the bottom line is traditional asymmetric crypto systems or even symmetric crypto systems are often impractical in this range. I mean, largely I would say that asymmetric cryptography, which employs things like 1024-bit RSA, or like, so these are typically more complex. Even elliptic curve, right? Essentially, when you are developing, which is a I would say like a high performance public key algorithm because of its shorter key size compared to RSA kind of crypto systems, but still often it's not good enough to suit these requirements. So just to give you some figures, if you compare a 1024-bit RSA encryption or signature versus a and corresponding AES operation, then you will see that it will probably consume something like 42 to 840, like megajoules to compare, millijoules to compare to something like 0.104 millijoules in the case of AES. So if you look at the communication energy, you'll see that 1024-bit block ciphers or symmetric key ciphers have got much lower energy compared to public key crypto systems. So of course, like this is always a question like how light is really light, and there are some interesting literature available. So I kind of like refer to one of them here, but there are many more such kind of survey articles and like reports to like address these points. So the broad design techniques, right? Essentially, as I understand, there are three basic approaches for designing ciphers for devices with constrained devices. The first one is, like when you're developing, say, optimized low-cost implementation of a trusted algorithm. So you probably take a trusted algorithm and you try to kind of adapt it to suit a specific platform. So you basically optimize it for the purpose. And also the other approach could be you modify a well investigated and trusted cipher, and you try to kind of make like you do not change the specifications. I mean, in the first case you do not change the specification, but you implement the specification as it is, but implement in a better way so that it has got less energy, low power, and probably consume less area. In the second direction, you can actually try to modify it even, like, so that it is more equipped to suit such applications. But at the same time, since you are making a modification, right, the security analysis or what is called a cryptanalysis becomes extremely crucial. And the third approach, right, is probably more has got richer returns, but at the same time is much more intricate because it requires expertise also, because where you are designing a totally new cipher with the goal of having low hardware implementation costs. So in this case, you have to know not only like the crypto, like of course you have to know the crypto, you have to know the cryptanalysis, but you also have to know the platforms, and you have to know like the engineering aspect along with. So therefore, right, I mean, some of the design criteria which are widely accepted is that you need to develop a cipher which is implementable in hardware and is expected to compute or in a small area requirement. So typically, previously people thought that lightweight block ciphers will work with 80 bits. Nowadays, 128-bit security are desired. They should operate on low power and low energy. Both of them are desirable. So which means that like you typically cannot do a strategy blindfold where you just make the computation less, but you like trade off that with large number of clock cycles, because if you're doing that, you're not really saving energy. So you need to kind of optimize on both power as well as energy. So lightweight is not, as they say, not really light plus weight. Okay, so light plus weight will mean that I will just like kind of delay the process and probably expend more clock cycles to attain lightweight block cipher. Moreover, right, many of these edge devices, people are nowadays seeing that they are amenable to side channel attacks, and many of these countermeasures against side channels, as I was trying to hint at in my previous talk, they have a huge overhead, something like 3 to 5 times, like blow up, and that essentially implies that you need to have lightweight cryptography which is also targeted towards like a low countermeasure or low cost countermeasure versus the physical attacks. So and also that the choice of the platform is also very crucial. For example, you can have different like ranges of platforms. So the ASICs or application specific in integrated circuits are a popular choice for lightweight crypto systems because you can choose your libraries accordingly. You can do mass productions, and that makes your per chip cost much smaller. But at the same time, ASIC design needs a lot of expertise, and at the same time, they also cannot be reconfigured or modified, and that has made FPGAs much more popular because you can reconfigure, you can upgrade them, you can do it in your lab. You have got more trust on the overall end-to-end design process. And nowadays, right, FPGAs have become pretty powerful, so that you have also have got good performance in terms of your implementation. So with the advent of recent low cost and low power FPGAs are becoming a major game changer. That is why you also see that Intel and other major companies are also procuring FPGA companies and making them as a part of their design cycle, because they are really offer like competitive or reasonably competitive platforms for implementing various kinds of implementations. So therefore, right, the FPGAs are also a popular choice. So the other important aspect when you are evaluating or doing your design is the corresponding performance metric. So for example, for comparison of performance, two basic needs are for lightweight cryptography are area, I mean, of course, and the throughput as well. So area is coming is at the forefront because you really want to make your design consume less amount of or require less amount of silicon. So you want to reduce the gate equivalence when you are implementing on ASICs. So gate equivalence is typically given in terms of number of NAND gates. Okay, so the number of NAND gates that would be required, and often they are referred to as GE or gate equivalence. And in FPGAs, the metric is in terms of slice utilization. So the slice means the fundamental component of an FPGA platform, which is often made out of lookup tables. So when you are implementing, you cannot really completely ignore throughput, because lightweight block ciphers, although you can ignore throughput to some extent, but they are still meant to be used in like applications which at least have got 100 kilo or operate on 100 kilohertz frequency. And the metric is in throughput is number of data bits which are encrypted per second in a frequency which is assumed to be around 100 kilohertz. Of course, like this, the choice of the frequency can vary depending on your platforms, but roughly you can take 100 kilohertz to be a pretty acceptable frequency. Then the other most important parameter is the energy consumption. So the energy depends upon the latency. The latency is often measured by the number of clock cycles and the critical path, which means the delay or the minimum clock cycle that you can settle for. That means the minimum time of the clock cycle that you can settle for, or which corresponds to the highest frequency at which your circuit will operate without giving any violations. So the corresponding energy metric is obtained by, like usually a thumb rule, which is like the average power multiplied by the latency and divided by the block length. So the block length is essentially the number of bits that you are processing at a given time. So these are very important metrics which you need to keep in mind when you are doing your design, and that will form also as a reference of, when you are comparing one implementation with another implementation. So here are some existing, a quick literature on some existing lightweight block ciphers on ASICs, and there, as you can see, that this is just a summary. So even here, you can see there are like many lightweight block ciphers that has been proposed. So you can see here that like there are, and I'll just draw your attention toward some of the most interesting parts. So you say AES still competes here, but AES is not necessarily the best choice so far as the lightweight block ciphers are concerned. In fact, there are these two ciphers like Present, which is a standard ISO standard of our lightweight block ciphers, which operates on 80 bits of key size and has got a block length of 64 bits, and is also right. For example, here you can see consumes something like 1570 gate equivalents and operates with a throughput of 200 kbps at 100 kilohertz. Likewise, there is another cipher which is called as Piccolo, which is an slightly improved version, which still operates on 80 bits of the key size. But yeah, sorry, the Present also has got a 120-bit block cipher version, and you can see that easily. If you, for instance, if you compare this with some of the other block ciphers, you will find that these ciphers have been designed in particular keeping lightweight as an important necessity. So one of the things that you will see, for example, there are some fundamental changes which the cipher designers make. For example, when you are making lightweight block ciphers, one fundamental change that you will see is in terms of what is called as the S box or the substitution box. So I will come to that in greater details during my talk. So the lightweight block cipher design is often platform to the sense is very sensitive towards the platform. Okay, so I'll just try to give you some quick understanding about why it is very sensitive. So suppose you are taking a design which works nicely on ASICs and would just like to directly port it on FPGA. So you can have very interesting surprises. For example, you can see here these are some of the lightweight block ciphers like Present, Memes, L block, and Piccolo. And you can see that the designers show that in ASICs, right, when you're giving figures in terms of gate equivalence, then present set takes 28 gates and MIPS takes 24, L blocks takes 22, and Piccolo takes 12 to implement the S box. So these are the figures to only implement one important component of the block cipher. But when you are implementing on FPGAs, all of them takes the same number of lookup tables. One of the reasons is because when you are looking into FPGAs, you will see that the internal structure is based on something which is called as the lookup table, and the lookup table comes with some fixed number of inputs. Okay, so even if you are consuming say half of that, or if you are consuming the full lookup table, you are still ending up in computing the entire lookup table. So your utilization will be still one lookup table. So therefore, right, when you are going from or say a platform which is like ASIC vis-a-vis a platform which is an FPGA, there can be some modifications that you need to do to your design. So what I mean like a summary is like if it is optimized for ASICs, need not be for FPGAs, and if it is optimized for FPGAs, it need not be optimized for ASICs. Another reasons why it is also true is you'll see that in the FPGA there are like the lookup tables which are used to implement the combinatorial part of your circuit, whereas along with it, right, there are some additional registers also, or the flip-flops, which also often if you are not using the flip-flops, then you are wasting them. So if you really want to make an like an optimized design which is nicely utilizing the underlying platforms, then FPGAs also offer very interesting design choices, which if you can understand, then that will help us to have better lightweight cipher implementations. So finally, like side channels, as I mentioned, is also very important, and I would just like to kind of refer to one refer to one comment from a paper which is from a group at KU Leuven in Belgium, which is also like the same group which made AES, or the worldwide AES standard. So they show that furthermore the area. So if you just read out this, you will see it talks about like furthermore the area of the second order. So this is like an S box implementation, and they are saying that they have taken a lightweight block cipher. So the lightweight block cipher, when they are implementing with side channel protections, is taking actually more number of protection bits or more number of gates which are required to protect an AES cipher. So what I mean to say is that suppose you have got two designs. Say suppose you make an AES design and you make a lightweight block cipher, call it as like lightweight cipher or LC suppose, and it may happen that like when you have got no countermeasure, then the LC, right, is essentially consuming less gates compared to AES. But when you want side channel protection, you also need to protect this, and you will also protect this. So this will probably have like some extra gates, and the LC will also probably have some extra gates. But it may end up that like when you are finally coming up with your protected design, then the protected design for LC is actually consuming more than what AES is consuming. So in that case, right, your entire design principle for lightweight block cipher goes for a toss. Okay, so therefore we also need to keep in the side channel countermeasure in mind, and in particular in lists in NIST's recent lightweight block competition requirement, one of the requirement was the ability to produce or provide it easily and at low cost is highly desirable. So it means like the side channel resistance is something that really is an important requirement in modern day designs. So what are side channels? I will be very quick here because I already talked in the last lecture on this. So side channels are basically covert channels which leak information which the designers of the crypto algorithms did not consider, and that essentially leads to like various kinds of attacks. So here is a very quick overview of an experimental setup. So you have got like your bunch of oscilloscopes, you have got your design under test, and when you are doing your operations, you are measuring the say the power consumption, the electromagnetic radiations around your device, and that essentially can be exploited by adversaries. So one of the reasons it can be exploited because the side channel computation, which could be the power consumption or the EM trace or even the behavior under faults, often depends upon the underlying computation that you are doing, and that leads us to attacks which are called as simple attacks. On the other hand, there are more complicated attacks which are called as differential attacks and more powerful attacks, which also exploit the fact, say, the power consumption of the device not only depends upon the operation, but it also depends upon the underlying data which you are actually trying to protect. So therefore, the idea is that if you are measuring the power consumption, then the power consumption can be essentially correlated with your secret keys, and you can trivially leak information. So this is a quick show, like illustration for some of you who have probably missed the last class, is that or last lecture. So like suppose you are taking a power trace for AES. So this is probably how the power trace for AES will look like. So you can see that there are very distinct signatures. Of course, to get the secret key, we need a bit of more of algorithms. So there are many algorithms, and one of the most popular forms of algorithms is what are called as the correlation power attacks. And I will not talk about this attack in today's discussion, but I'll just say that power consumption can essentially be correlated with your real power trace that has been like the power that you are observing can be correlated with your secret key guess, and if the correlation is high, then you probably you probably say that the guess that you have made is good. And the good thing about these attacks are these are based on divide and conquer attacks, which means that even if you have a block cipher which has got say 2 to the power of 128 bits of security, using this kind of attacks, you can reduce it very fast to something which is proportional to the power of 8. So you can see that there is an enormous reduction in terms of the entropy, and that leads to very real life attacks, which makes designs against such kind of adversaries extremely challenging. So how do you protect against side channel attacks? Okay, so one of the most popular forms of protections against side channel attacks are what are called as masking. So masking means you basically try to randomize your computation, and then you try to de-randomize the computation so that eventually the result is as per specifications. But if the attacker is observing the power trace, then he or she cannot correlate it with your actual information. So one of the classic forms of masking is what are called as threshold implementations, which are based on a very interesting combination of secret sharing and multi-party computation. So I will try to give a very quick overview behind the idea of such kind of countermeasures. So the first, let us try to understand how masking will work. So in a normal scenario, right, when I'm trying to do a computation which is say Q equal to A into B, I want to do this computation. And if I do that in a very trivial manner, as we have discussed, then by measuring the power consumption, somebody can obtain the secret informations like A and B. So you can have a very strong correlation. Now, in order to break that, you try to introduce masks in your design, and these masks are typically obtained by from the output of a true random number generator. So these masks are random bits that are generated. So in this case, for in the example of this multiplication, imagine that there are two masked bits like MA and MB, which are randomly generated and are used to mask the actual data, say A and B. So you kind of hide the information inside this mask, and as you know that if MA and MB are chosen from a very good like random source, then your information of AM which you are generating is essentially statistically independent and uncorrelated with your actual data A. So now you have to do your computation inside the mask. So you kind of hide behind the mask. That means you have to kind of rewrite the multiplication using only AM and BM, and that is not very difficult to see. So here is like an architecture which essentially does that. There are of course many small nuances in this design. For example, as a VLSI designer, I may be very much tempted to like balance this circuit, and that can actually open up interesting attack vectors. So but anyway, the point here is that I would take like this circuit, and the whole what the circuit will result in some value of QM, and this QM essentially is nothing but the final Q, but it has been masked by some random bit. So if I take this QM and if I take this MQ, which is a mask, and if I XOR them, then I will get back the original Q. but the entire computation is done with these masks or under these masks, with the idea of that this will protect us against these power attacks. But there is a cost. You can see that to implement a single AND gate or a multiplier, you need now 4 multipliers and you need several XOR. So you can see that there's an enormous cost when you are going for such a protected design. So, but moreover, on top of that, there is another problem. The problem is, as you know, that most of the circuits or VLSI circuits are prone to glitches. And again, without going into details about that, I would like to mention here that because of the underlying glitches, people have shown that even with these protections, you need more observations. Probably, you need something like 1 million observations. But even that, right, is using that you will be able to get the entire key. So that means like you are still not with these masks even paying so much, right? You are not able to get protections against an adversary who is able to observe like sufficient amount of power traces. But and moreover, right, I would like to mention that the security that you are getting, even if you are observing say 1 million observations, is much lesser, much lesser actually, okay, which is compared to the amount of security that the AES would typically like to provide you. So the security that we would like to provide you is something like 2 to the power of 128, proportional to the power of 128. That means that an attacker, right, who wants to get the key needs to do something like 2 to the power of 128 computations. By just to give some numbers in perspective, 2 to the power of 80 is more than the number of particles in this universe. So you can see that 2 to the power of 128 is really a very large number. So if I tell you that you are able to do the attack with say 1 million observations, right, it will probably take you a couple of days, but still that is not the amount of security that we would like to have in our systems. So therefore we need kind of protections, and one of the ways of doing that is this nice technique which are called as threshold implementations, which are based on a very interesting combination of multi-party computations and secret sharing. So multi-party computations essentially are the basic technique of TI, or as it is abbreviated, are based on 4 properties. The first one is of course correctness, which means that you still need to get the same algorithm working, and along with it you also need to have these requirements of what are called as uniform masking, non-completeness, and uniform sharing of a function. So the idea here is that if you want a protection against an adversary, we call this as the dth order adversary, which means that an adversary who is observing, say, who is basically taking the power trace. So imagine that this is the power trace, and doing statistical analysis on D points simultaneously. So the idea is that if you are observing D points, then that is equivalent to as if you are taking the chip and you are basically probing at D different points. Okay, so this is called as the probing model, to quantify such kind of attackers. So now the basic idea behind this is as follows. I mean, I'll again give a very top level idea. So suppose you want to implement a function fx, okay, so how do you do that? You take x and you break it up into shares. Suppose I break it up into say, like x or sx shares. That means I will basically create something like x1, x2, and so on till say x sx, so that if I XOR them, I get back the original x. So now the entire computation will be done using these shares. Okay, so I will be doing using these shares, but I will ensure that, I mean, I will be provide, like defining something like f1. I will be defining something like f2. All of them, like let me say f1, f2, and so on till fs. Each of them will be operating on some of these shares, but not all. Okay. The idea is that if I finally take f1, f2, and if I XOR them, then I should get back the original fx. So you're basically doing your computation in shares, ensuring that none of these functions operate on all the possible shares. And now you are banking on the fact that even if out here I am observing say anything which is lesser than sx amount of observation, then I have got no information about x. So you are basically trying to give an information theoretic security against the adversary. So here is a quick example to kind of like perceive that. So we want to implement a equal to x into y, but you see that x has been decomposed into these 4 shares, y has been decomposed into 4 shares, and now I am defining these functions, as I said, f1, f2, f3, f4. Here we have denoted as a1, a2, a3, and a4. So these are the corresponding functions. You can think of this to be f1, this is f2, this is f3, and this is f4. So that finally, if you combine a1, a2, a3, and a4, you will get back the original output, which is x into y. So that is the basic idea of TI, but you can easily observe that there is a huge amount of cost that is accompanying along with it. So therefore it is sound, but it is a costly protection. Okay, and the question is, right, I mean, and if you really want to have, you know, the more the algebraic degree, more the number of shares that are needed. In fact, there is a result which says that if your algebraic degree, which means that the number of n terms that you have in your Boolean expansion of a particular output, the number of shares will be +1. Okay, so if you have got an algebraic degree of d, you need d+1 shares to protect your design, which means that if you have got a quadratic Boolean function, you need at least 3 shares. If you have got a cubic Boolean equation, you need at least 4 shares, and so on. So the bottom line is, like, can we build ciphers from simple rules which are easy to protect? So here comes the idea of cellular automata. And I think that before I go into that, I mean, I will be trying to give you a very quick background on block ciphers. Okay, and then I will come to this. So that the whole point is that when you are designing a lightweight crypto cipher, right? I mean, you have got different endpoints. Like you can choose something which is very efficient to implement. Okay, and while you are doing that, you may end up, you know, like going in front of a dragon who is your adversary or the attacker. So it's a very, you know, like, I would say, a tricky design choice of being. So there is a saying. This is a, you know, like, from the fable which talks about Scylla and Charybdis, like, where there is a one rock on the other side, and there is, if you want to avoid that rock, you go close to a dragon. Okay, so you have to make your design choices, and the margin of error is really, really very narrow. So this is the classic overview of the cryptographic computation, where you have got the encryption device and you have got the decryption device, and you would like to typically employ block ciphers to achieve that. So the block ciphers, if you look into that, are basically nothing but crypto devices which are built on encrypting blocks of data, which operates on secret data and provides you with the corresponding ciphertext. So when we talk about AES, then the block size that we have is, say, 120 bits. Okay, so you are typically operating on 120-bit blocks, and maybe 120-bit of the key to give you something which is like AES 128. Okay, so of course you need a decryption, and then, you know, like, you have got different rounds inside. The idea of the block cipher is actually built on rounds, so they are iterative block ciphers. And there are two important components inside the block cipher, which provides us with the much needed requirements of confusion and diffusion, which was originally proposed by the great Claude Shannon, and showed that how you can essentially obtain an overall resistance against various class of attacks. So I will be very quick here, but rather try to kind of narrow down towards an important two blocks. One of them is what is called as the S box, or the substitution blocks, which tries to kind of provide us the much needed non-linearity to the cipher. So gives us the non-linearity. And the other one is what is called as the P box, or permutation box, which provides us the diffusion. That means, like, if there is a small disturbance, or there is a change in the input, that should kind of diffuse inside the block cipher. So the fundamental principle is based on what is called as the Kashkov's principle, which means that the crypto system is known to the adversary, but the secrecy is relying on the secret key, and cryptanalysis is basically the art of obtaining the key. So the first important puzzle piece that any block cipher designer needs to satisfy or understand is the design of the S box, which is essentially the much needed block which gives us nonlinearity to the cipher. So typically, any block cipher or any S box that I choose, let me call this as the S box, is nothing but a vectorial Boolean function. That means it will operate on, say, n inputs. So if I write it as from x1 to xn, and will provide us outputs which are like y1 to yn. So each of them are Boolean functions like f1 to fm, but they have got very strict requirements because of the requirement of nonlinearity. So a Boolean function, if you look into that, will probably look something like this. So this is a Boolean function of n variables written in the form of what is called as the algebraic normal form, or ANF. So you have got in the ANF form, you have got n terms. So these are your n terms, and the pluses here are nothing but the exclusive ORs. So when you want to make a block cipher or any cipher of this type, you will see that these n terms are what gives you the nonlinearity, whereas the XORs are essentially often referred to as the linear terms. Okay, so they give you just linearity to your designs. So how is nonlinearity defined? So I will be again giving a very top level and quick description or definition of nonlinearity. So it means, like, suppose I've got a Boolean, two Boolean inputs like x1 and x2, and I want to kind of propose a block function which is, say, x1 or x2. So this is the corresponding truth table as I know of x1, x2. So how do I measure the nonlinearity of this function? So what I do is very simple. I check all the possible linear functions in terms of x1, x2. So it could be the zero function where it is all zeros. It is x1, it is x2, and in this case, it is also x1 XORed with x2. As I said, that if you are only using XORs, it's a linear function. So now what I try to do is I try to take the distance of the vector of the Boolean truth table of this function with all these possible linear functions, and the minimum value of that distance, right, is what gives me my nonlinearity. Okay, so therefore in this case, as you can see that this distance is 3, this is 1, this is 1, and this is 1. So I will say that the nonlinearity of this function is 1. So that is how I define my nonlinearity. Now it is a very challenging task, and there are many works, many very interesting works which have been done on designing good Boolean functions. The problem becomes very complex when you are increasing the number of input bits so that it is equally distant from all the possible linear functions. So you can appreciate that if you have got n variables, so in this case you have got 2 variables, so there are 4 linear functions. If you have got n variables, you will have 2 to the power of n linear functions. And you will see that it is very tricky, because if you are going, like far away from one of the linear functions, you will probably go close towards another one. So you need to make your design so that you are appropriately placed from all of them, and that is the motivation of having this minimum as the requirement of like computing the nonlinearity of the Boolean function. So here is again the same thing written in a little bit more fancy way, so we can ignore that. The other important requirement is for any good SBox is what is called as the avalanche criteria, which means that if I make a small change to the input, there should be a huge amount of change to the output, and there is a strict formal definition which is called as the strict avalanche criteria. So now we want a good SBox design so that it should be protected against cryptanalysis. The two most important forms of cryptanalysis, or the starting cryptanalysis, are what are called the linear cryptanalysis and differential cryptanalysis. Okay, so this is called as linear cryptanalysis, and this is called as differential cryptanalysis. So I'm not going into details, but I would like to say that just keep in your mind that it is very challenging when you are computing an SBox, because it is not only that every Boolean function should satisfy requirements, like have high nonlinearity, satisfy avalanche criteria, and so on, but even their linear combinations. That means if I say take f1 and if I take f2 and I want to calculate say f1 XOR f2, should also satisfy high nonlinearity and so on. So therefore, right, that's why the design problem of making a Boolean function is even more complex when you are designing a vectorial Boolean function with those requirements. So therefore, the good SBox is defining or designing a good box is even more challenging, and is one of the most challenging puzzle pieces for lightweight cipher designers, because you have to make it lightweight at the same time satisfy these requirements. Further, another requirement that we try to kind of look into is in terms of the side channel protection. That means I want to make my design so that it is also less costly in terms of implementing the countermeasures. So what is the criteria of good SBoxes? So here is a quick summary of that. So you need balancedness, of course, which means the equal numbers of zeros and ones. You need to have high nonlinearity of the individual Boolean functions, and also high nonlinearity of their combinations. It needs to satisfy the strict avalanche criteria, have got a high algebraic degree, and so on. So now we would for instance, like just to give you an example, like this could be a like an SBox of one of the lightweight block ciphers which is present, as I said. So you can see that here it is made out of two functions. Like there is one function called f and there is another function called g, and the SBox is made out of a composition of these two functions. So just for an example, I just show you the Boolean function for f. So you see that this f3, f2, f1, f0 corresponds to only this function. A similar function is also for g, and together they make the SBox of this cipher. So now what is the purpose of, so if you look into AES, for example, you will not see such kind of definition of the SBox, okay? But here you give these definitions. For instance, like you try to break the SBox into two components. One of them is f and the other one is g. So if you look into f, for instance, which is shown over here as f0, f1, f2, and f3, you will find that the maximum algebraic degree, right, that is over there is 2. So now if you want to bring in a side channel protection, as I said, you need a countermeasure where there are 3 shares, okay, which makes the cost reasonably controlled. But if you look, for example, if you just combine f and g, and then if you apply a side channel protection, then you will probably need 4 shares, and that makes the design much more complex, okay? So finally, right, good SBox design is not good enough. because you also need to have the diffusion layer, because the objective or the purpose of the diffusion layer is that if you have got a small disturbance introduced into this S box, for example, the diffusion layer, if it is good, right, it will spread you to all the possible S boxes. So the number of active S boxes will become more, and that will make attacks much more difficult. So you also need to understand how, for example, here, as you can see here, that one of the S boxes have been affected, but because of the diffusion layer, which is made very nicely, you see that this diffusion spreads to this S box input, this input also spreads to this S box input, and finally it spreads to all the output S boxes. Okay, so typically, as the avalanche criteria says, if I make a 1 bit change, then approximately half of the output bits should get changed. This is the necessary condition, but again, I would like to mention that it is not a sufficient condition for the overall security. This is at least important. So here comes, like, so now I want to make these S boxes and, like good internal blocks, which are not only like good in terms of robustness, but also are, like easy to protect with side channel countermeasures. So this brings us to this, nice primitive, which are called as CA. So of course, I'm sure that for in this DAS, I do not need to kind of introduce a CA, but the way we kind of see the CA here is that we try to see the CA as, like a mapping, I would say, like from say n bits to n bits, such that each of the bits are essentially made out of local roots. So what I mean is that suppose I want to make a 4x4 S box. Okay, so the idea that I try to exploit here or explore here is that, as you can see here in my previous present cipher S box definition, each of the functions were different. So the first thing that we try to do is that we try to make this f function using local rules, okay, which is like one of the major selling point C of the CA. So it is made out of very simple local rules. And the second thing is that I wanted to make the function so that each of the components are essentially the same. So in that case, I will just implement one of the functions, but then use it to get the other component outputs. So the elaborate description of this paper is published in this conference, or like also this journal, which is called as ISER Transaction on Symmetric Cryptology, which is the de facto standard conference for publishing works on block ciphers. It is also abbreviated as FSE. So we try to kind of like look into that, and I would try to sort of say that there are many ingenuine works which have shown how a CA structure would look like, and I do not really want to go into the details of that. So we have got like excellent results which shows that how you can make complex patterns using simple rules. But then what I have found out also is that when you are using those simple rules to make like in particular cryptographic constructions, then there are some additional challenges which we need to mitigate. So here was an old attempt that I made once of like trying to make a CA based SBox design, which was published in IEEE Transaction and Computers in 2011, where I suppose want to make an like say, so in this case an 8x5 function. We can make it any work for any n×5 function, also any n×k function. So in this case we choose a 5-cell maximal cell CA, which has got some rules like 150, 159. So the paper exactly talks about why those rules are chosen. So this is the corresponding function that I choose here and use it to create this construction. Note that this is not a bijective map, and many of the block ciphers need bijective map. There are other examples where n×k also can be used, in particularly when you're using Feastel kind of constructions, which is there in the DES family of ciphers. So in the very top level, right? How does this SVA or Boolean function lookup look like? So what you do is that you take the input Z. So suppose this is your input Z 156 written in form of binary. You can read that this is nothing but binary, and there is a matrix that we define which is called as W. So that the choice of W is motivated by the fact that you need to satisfy the strict avalanche criteria, and then you multiply W and Z, okay, to get something which is shown here as Z dash. So now what you do is you break that up into two parts. So one part is called as the first part, which is essentially, as you can see here, in this case it is 4. So this is the corresponding value which is shown here as 4, and the remaining part which is called as 3. So now when I want to compute the lookup for 156, so what we do is we do it in this manner. So we basically take the maximal length CA, which has just been defined, and the characteristic matrix for which is T, and the power or the number of times you are applying that essentially is controlled by this input, and the input to that is given by this input. So in this case, it is T43 that you need to compute. Okay, and that will give you the corresponding output 192 in this case. So we have elaborate proofs in the paper which shows that it has got nice cryptographic properties. So this is one thing that I was always like very intrigued, like how you really can make mathematically provable nonlinearity, because when you're wanting for ciphered implementations you need lower bounds in the nonlinearity. In this case we can prove that the minimum nonlinearity is 112, which is very high. Maximum for 8 variables is 120, but in those cases they are not balanced. In our constructions it is also balanced. It has got a degree of 4, and in fact any non-zero combination of the balanced functions you will see will have a nonlinearity of 112. It has got a very high resistance against differential cryptanalysis, and also every Boolean function will satisfy the strict avalanche criteria. However, one of the problems that we had in this construction is also in terms of the overhead, and more importantly, in how do you really make bijective S boxes or one-to-one S boxes. As you can see here, this design was an n cross k construction, okay, where k is greater than n by 2. So you can make pretty large mappings, but and also, right, you can show that the growth of the resource is pretty polynomial and doesn't really explode quadratically with respect to the inputs. But still, right, you cannot make bijective mappings using this construction directly. So recently, in 2018, we had a paper where we tried to kind of make such kind of bijective mappings. So in this case, we basically chose or started with a simple function, which essentially is built on local rules. Okay, and using that, we wanted to construct 4 cross 4 S boxes. So there are several 4 cross 4 S boxes that we looked into. So as you can see here, this number is given over here, and out of them, we found that 512 instances which were optimal. So optimal means in terms of their nonlinearity and other requirements. And the good thing about these constructions were now that you have got one single function, which I called as f, which operates on say 4 inputs. And now what I do is I take the input and I do a cyclic shift to the input. Okay, so suppose it is x1, x2, x3, and x4. Next time, right, it gets a cyclic shift, and then the next then now if I compute f, you get the next output bit. And again, if you give a cyclic shift, you get the next output bit. So basically, you are spending say 4 clock cycles, but only with one single function that has got implemented. And later on, right, we use it to get the overall design. So of course we try to kind of evaluate this design under various kinds of like analysis. You need to, so we made basically, here is a table which talks about like the summary of these functions. As you can see that these are built on nonlinear functions, but all of them are operating only on 4 neighborhoods. That means they're all operating only on 4 local variables. And I kind of like summarize here or rather group these functions in terms of the number of cubic terms, number of quadratic terms, and number of linear terms in their Boolean expansions. As you can probably anticipate, is that if you are at the top of the table, then the cost would be less, and if you are at the down of the table, the cost would be more, because of the cubic terms are essentially what more dictates the amount of cost in terms of the gate equivalence. So then we take this design, and we also find out that these rules are pretty easy to do threshold implementations or protect against the side channel adversaries. And finally, we come up with this design of the side channel protection. But there is a trick that we need to kind of employ here. Not that you take this function and directly apply the TI, because if you do that, then you have got a 3-degree term. And if you apply a TI protection, you need 4 shares, which is very costly. But rather what we do here is, so therefore here is a quick overview or comparison of the amount of area and power of these constructions vis-a-vis equivalent. If you compare it with present, you have got something like 450 gate equivalents. The amount of improvements in terms of the power is also quite significant and promising. So however, if you want to go for a composite implementation against this, what we do is, rather than implementing this function straight away, we actually decompose this function into 2 functions. As you can see, each of these functions are quadratic functions. So now you can implement them only in 3 shares, which is 2 plus 1. So that is the idea that we try to employ here and come up with a composite TI architecture where each subfunction has got degree 2, and therefore you can implement that with 3 shares. And if you do that, finally here are your results of the overall cipher. So you can see that the cipher overall, like, or the S box in particular, takes pretty less gates and also consumes less amount of energy. Remember, all of these S boxes are actually protected against side channels, which means that if you try to implement this, and in our case, we took something like, say, 10 lakh power traces, and we found out that there is a standard test for side channel inspection, which is called as the TVLA, which is essentially called as fixed versus random test. So I will not again have the time to go in details behind this, but in an overall idea is that you take any cipher and you give two types of inputs. In one case, you give random inputs, okay, and you measure the power consumption. And in other case, you take your design and you give a constant input, and you again measure the power distribution. And now you take these two distributions and apply a student t-test and see that if the distributions are, or the t metric or t statistic is more than a threshold, then you see that there is a potential leakage. So this is a worldwide standard which has now been standardized also by several standardization bodies, which tells that your design should essentially ensure that with sufficient number of observations, the t value should be less than a threshold, which is told to be as 4.5, which gives you a reasonable amount of confidence. With a confidence, you are able to say that potentially your design does not have any exploitable leakages. Or more, rather than saying it doesn't have exploitable leakages, it's better to say that if your threshold is more than 4.5, there is a threshold, there is a leakage. So you need to ensure that there are no evident leakages in your design. So this is an extremely important result that you need to provide for any side channel protections. So with the CA-based S box, with this protection, we were able to demonstrate that there is no leakage. As you can see here, the thresholds here are much lesser than 4.5. So you are well within the boundaries to show that the CA essentially can be employed to get not only lightweightness, but also protections against classical as well as side channel protections. But then when we wanted to make a complete end-to-end block cipher, which we called as triple initially, but we faced a problem with this. Okay, and I will again talk about the problem very quickly, and that basically brings us to the other piece of the puzzle, which is the diffusion layer. So you also want to make a good diffusion layer to ensure that you are secured against various other attacks. So a block cipher with a weak diffusion layer has got critical security vulnerabilities, even if you have got a strong S box. So the way in which you implement linear transformations often are depicted in the form of a matrix, which means like you take a matrix and you take and you essentially take your inputs and you basically do a multiplication. These matrix elements are often implemented in the Galois field, say GF to the power of n. So just to give you an example, so if you look into AES, the diffusion layer is implemented by a transformation which is called as a mixed columns. So what you do is you take the AES, so these are your AES state, so these are 120 bits all organized in terms of 4 columns where each column element is a byte. So what you do is that you take one of these columns and you multiply with this matrix. So this matrix has been very carefully manipulated. So in fact, it borrows its ideas from coding theory and actually is what is called as a maximum distance separable code. So which means that just to give you a quick perspective or the criteria of this design, so it needs to satisfy a requirement which is called as a branch number. Okay, so what does it mean? It means that if I, for example, employ a one byte difference to the input of this matrix, and if I consider the number of output disturbances that I will get, so if I indicate this as D1 and if I indicate this as D2, you can prove that in context to this particular choice of the matrix, D1 plus D2 is greater than equal to 5. So that means if one byte gets disturbed here, then 4 of the bytes are getting disturbed here, because at least 4 bytes, right, must be disturbed here to ensure that D1 plus D2 is greater than equal to 5. So that means a single bit difference in a byte will propagate to the entire column because of the choice of your mixed column matrix. So that brings us to this branch number, and but unfortunately, right, I mean, it is very costly to implement, and therefore we do our designs with something which are called as almost MDS. So in almost MDS, you just change like a little bit, and you can actually do the almost MDS implementation only with matrices which has got only zeros and ones. That means they are binary matrices. But then since their branch number rather than being 5 is 4, it means that if you make a 1 bit change, then there is a chance that 3 output bits will get propagated, and one of the output bits is still not affected. So in order to do away with that, you have to increase the number of rounds, and that will also have an effect on the overall performance. So therefore, right, I mean, when we looked into our CA, we found that everything was good or CA based SBox, except the problem that was we found out was that the branch number was 2. So that the branch number is 2, which means that if I take the SBox, okay, and if I disturb one of the input bits, then there is a chance that only one bit in the output gets affected. If its branch number was, for instance, 3, or like in usual constructions of when the branch number is 3, which means that if you are affecting one input bit, then at least 2 output bits will get affected, and that helps you to propagate the diffusion much faster. So therefore, so here is a quick demo, just to visualize that you have such kind of scenarios. So therefore, there is a problem. The problem is that because of this, if you take a very simple diffusion layer, which is shown over here, and if you disturb like one input bit, there is a chance that one output bit gets propagated, that spreads, and it remains only in one S boxes. So if you have got, say, R rounds, then you can easily see that only R S boxes will get affected, and that essentially makes designs or designs susceptible to various kinds of cryptanalysis. So therefore, there is another attack scenario also, which I will not get into details, which is called as the invariant subspace attack, and we need to also protect against such kind of attack vectors. So now, in order to protect this, finally we come up with a very strong, linear layer, and the linear layer essentially is built on what is called as an almost MDS matrix. Okay, so I will again, so just to give you an perspective, it is the same CA based SBox, except that now you have got this almost MDS protector along with, which ensures, and that is why you need this almost MDS layer, which has got a minimum branch number of 4, so that even if there is a 1-bit disturbance that has been propagated here by this SBox, because of the definition of this almost MDS layer, at least 4 output bits gets affected, and that helps you to kind of have sufficient amount of diffusion to protect against various classes of cryptanalysis. So finally, if you combine all of this, you will see that this gives you a very lookup tables, and it can help you to there will be a slightly increase in terms of latency, but that is sometimes like a design choice that you always need to make when you are making your designs which are adapted for lightweight platforms. So this is the final proposal that we are trying to work out. So this is still a work in progress, which is called as LBT64, which is based on this underlying Cellular Automata based SBox. These are some of the design pieces that we have. And of course, now we proved that we have got sufficient amount of cryptanalysis against protections against differential, linear, invariant subspace, and other forms of cryptanalytic attacks. So we also protect our design end to end against side channels, and I will not go into the details, but finally just show you that our design is well within the threshold, as I mentioned, which is called as a TVLA based t-test, to show that the overall design is secured against side channel adversaries. So to conclude, I try to kind of motivate lightweight cryptography design choices, and mention that it is platform centric. Side channel attack countermeasures are very important. I try to kind of propose a lightweight strategy to design SBoxes using simple rules, which essentially CA provides us, but we also try to equip with various kinds of requirements to have an end-to-end protection. We also try to protect it against using a technique which is called, which is largely based on the TI based method or threshold implementation based method, to come up with a complete end-to-end proposal for a lightweight block cipher, which we call as LBT64. So with this, I would like to say thank you for your attention, and if there are any questions, I would be very happy to address.
Is there any question?
Okay, I have a question. You know,
Sure. Yeah.
actually, so you talked about Cellular Automata. So my general question is, what is your feeling? The prospect of Cellular Automata in developing say, hardware security and all. So what do you think? How good it would be? I
So,
mean,
my personal, I have also been trying to apply CA for various kinds of cipher constructions. So what I feel is that CA definitely offers, and in fact, I mean, just to give like some like I think encouragement. I think there are some interesting constructions which are actually kind of borrow some ideas from cellular automata also classically. Like for example, if you see that current hash function which is called as sketchup, I find that there are some very interesting like inputs from the CA based construction. But one thing that I would also like to, and this is something that I have learned in the hard way also to some extent, is that you have to like try to kind of push these ideas in front of a crypto community and try to get ratified, like so that that although there are nice benefits in terms of the cellular automata constructions, but they also need to kind of like be equipped with additional things or additional constructions so that they are resistant against the adversaries. Because although the CA has been like very promising in terms of like providing the pseudo randomness which are used for other applications like testing, but the pseudo randomness that we need for cryptography is fundamentally different from that actually, and that essentially like has led to like probably some exercises where the CA has been employed and also has been cryptanalyzed or broken because of the fact that often, right, the pseudo randomness that is needed for protecting against these adversaries have not been that so I would rather say so closely monitored actually. So if you are doing that, then the CA, I feel that in particularly in terms of the diffusion has got a lot of advantages. The other problem that the other challenge that I see is also because of the fact that we know that the nonlinear CA, which is there, right, which basically provides us nonlinearity and also provides us diffusion, is pretty hard to kind of characterize actually. So that essentially makes it because one thing is that when you are applying anything for cryptography, we need to analyze it very well actually. So if we are able to make like progresses in nonlinear cellular automata which are also which have also got good mathematical analysis in terms of providing say lower bounds of nonlinearity and so on, I'm sure it will have more impact.
Okay. Another question. So in your work, what you have done, your neighbor dependency from 3 to 4 you have extended. Huh? So
Right.
so my point is, if we extend, so classically traditionally people work with non-uniform ECA, that all the cells they use ECA rules, all from 3 neighborhood rule. Okay.
Right.
But if we go to say 4 neighborhood dependency or 5 neighborhood dependency or beyond of that, so can you get an advantage in in your case?
Yes, actually, right now I'm trying to work on a 5 neighborhood dependency actually. Okay, so there I can say that like there may be some interesting things that can come up. Which, for example, as I said, right, I was not able to using 4 neighborhood. I was not able to find out any rule actually out of the 6,000 something rules that I saw, right, which essentially had this requirement of like branch number being say 2. So all of them had a branch number which is a, all of them had a branch number 2, which means that if I take the Boolean function and if I just disturb one of the input bits, then output, right, there are like at least one output bits which are getting affected. But what I want rather in terms of security or cryptographic resistance is that if I vary a one input bit, then at least two output bits should get affected. So as you say, sorry, that when you are looking at cellular automated rules which are working on like higher dimensions, maybe we will be able to get those kind of rules as well. So although like in classically I would say that when you are going for higher dimensions there are some advantages, but we need to look at the advantages from the point of view of cryptanalysis. So that is essentially something that probably has not been done as of now so extensively.
Thank you. Yeah, got your point. Okay. Thank you. Yeah. Sumit.
Sir, I have a question, sir.
Yeah, sure. Yeah.
Basically for design of S-box, your work that means you are used the maximal length cellular automata. That means where the cycle length is 2 to the power n-1. But also for the like non-uniform cellular automata are also used for design of some Xbox. Which are not maximal length. So basically, the what are the advantage of maximal length cellular automata over the non-uniform cellular automata which are not maximal length? So
Okay,
design of S
so
box.
maybe I think maybe I like I mean I just say my point of view, and it may not be like completely accurate as well, but my understanding is that when you are using maximal length CA, you can know the CA very well because there are such nice characterizations which are available. Okay, so what I tried to prove in that paper, which is now a pretty old paper, I think 10 years old paper or so actually, but I had tried, like a huge, before that I had tried several attempts, like of applying CA to get a lower bound in terms of nonlinearity, but unfortunately I was not able to do that. But in this construction, if you read the paper, right, you will see that there is a proof which gives you the nonlinearity lower bound actually, and shows you that even if you take linear combinations of those vectorial functions, you still get a lower bound of the nonlinearity. So that is very important. Okay, even if you are using a nonlinear maximal length CA, and if you are able to get that lower bound in terms of the vectorial functions and also the combinations, then I think you can use it actually. But I to the best of my knowledge, could not find such nice characterizations of the nonlinear CA. I tried to do some of them myself also, but I really was not so successful in doing that, I would say.
Thank you, sir. Thank you.
Sir, I have one question, only
Yeah,
a
sure,
very basic question.
sure. Yeah.
So, what you were saying is, if there was some way to characterize this nonlinear CA, just like you are doing, just like for matrix algebra is there for linear CAs. In
Yeah,
that case, it might be having more scope
usage.
of
Yeah,
usage and improvement, maybe because you are using linear CA to get that non-linearity bound. Maybe
right.
if there was some possibility of non-linear CA itself, then maybe you will be getting better bound, or
Yeah.
maybe there will be more scope. And one thing I want to ask you, what about, like, I work in random number generation only, and
Mhm.
whatever I have studied so far, all
Mhm.
this like none of the random number generators are cryptographically secure. And
Mhm.
this, what about this statistical test? What do you think about the statistical test? Is there any use of that in the in cryptographic purposes, like this NIST or something?
Yeah, so that's like I mean understanding random numberness I think is a $1 million question actually. Okay, so my understanding is that if you take the standard NIST test, for example, or even nowadays there are some German tests which are called as AIS. Okay, if you take those tests, then all of them are necessary conditions. They are not sufficient conditions in terms of randomness. Okay, so what I feel, or what I have understood by listening to experts who work in true random number generators, is that you cannot make any randomness, right, out of pure software. You have to rely on some kind of non-determinism in nature. Like it should be, like noise, which is, like embedded in your systems. Using that, you can create a small seed, which is an output of a TRNG, and you can use it along with a, like CA-based technique or something like that, where you can actually expand it to get what is called, what is called as a pseudo random number generator. But the seed, or the fundamental seed, right, has to be from some kind of non-determinism of your computer system. Okay, so we tried some of the ideas, and I'm still working on that. So something, like where you can create a TRNG using an FPGA, for example, creating some kind of, like delay elements inside the FPGA. In one of our works, which we published in COSET actually, where we tried to show that the interrupts, for example, that are there in your computing systems can be used to trigger a true random number generator. And interestingly, in that paper also, I use a follow-up cellular automata, if I remember correctly. Okay, but the seed, right, has to be from some kind of noise source, and that cannot be from such a well-structured component like a CA, because in CA you know everything, right? If you know the inputs, you know the output. It's a deterministic function at the end of the day.
Okay, but sir, for zero randomness, you have to, like, the seed has to be reproducible, right? But if we get this from non-deterministic, will that be reproducible always?
No, so when you want to make a TRNG, right, you don't need to make it reproducible, because the TRNG should ideally not be reproducible. Okay,
Okay.
it is random. Okay, but even in a PRA, like a pseudo random number generator, right, I mean there is no requirement of any reproduction as such, because it should be like completely uncharacterizable and unpredictable.
Yeah, but okay. So in cryptographic purposes, we don't have the need of this reproducible
Yeah,
same
yeah,
sequence. to be
Yeah, I'm
reproduced.
talking. Yeah, I'm talking with that perspective. So if you look into the definition of a TRNG as the PRNG, right? It just means that if I take a source, which is a random source, and if I take the output from my system, I should not be able to design a probabilistic polynomial time algorithm which should be able to distinguish between these two sources. That is the most fundamental definition of a random source, actually. Okay. So there are some universal tests which gives you a universal definition of such a randomness source, but I don't think none of them, right, can be built out of things which are you need that entropy, right? So you need to have then the entropy source can only come from nature. Actually, there is no other way, as far as I understand.
Okay, sir. Thank you.
Is there any other question? Not been
Yes.
there.
So if you want, if there are like follow-up questions, please feel happy to like shoot emails. I mean, I just want to mention that in my email I forgot to make that change. That erna.in has got changed into ac.in. So please, you can if any of you are interested, you can send your questions on there.
Thank you, sir.
Thank you.
Thank you so much.
Thank
Yeah.
you. Thank you.
Bye.
Thank you.
Bye. Bye.
Thank you, sir.
Thank you. Bye.